Okay, good morning, everybody. Thank you all for coming to our special ISOA colloquium this morning. I'm pleased to introduce our speaker today, Professor Dan Leaf, who is coming to us from Clemson University. She has been there just a couple years. Before that, she finished her Ph.D. at Georgia Tech and a master's degree in statistics, and before that, from her BS from Tsinghua University. She, in her brief career, is already accumulating many awards, including some Best Paper Awards from IISE, I think. But most recently, as of this morning, has been recommended for a career award from NSF, so that's a fantastic news as well. So congratulations and welcome. Yeah.
Great, thank you so much for the warm introduction. It's my pleasure to be here to share with you some of my recent research on integrated cyber-physical security and resilience of manufacturing systems. So the manufacturing systems I'm working on, that I'm investigating, are what I call IoT-enabled manufacturing systems, Industrial Internet of Things enabled manufacturing systems. And it actually includes a very broad of manufacturing processes, like assembly processes, metal making processes, pharmaceutical manufacturing, things like that. But they all have an integration of the cyber and physical components, the smart sensors, distributed control systems integrated with the physical process. And a better definition would be these systems, they involve multiple processes working in synergy through both physical treatment and digital communications enabled by the smart sensing and control technologies. And these systems are becoming more efficient because of these new technologies and highly motivated, but that also caused them to be more vulnerable to cyber attacks. And they also have a very low tolerance because of the highly automation to operation disruptions caused by these cyber attacks. And that's why more and more attention has been driven to manufacturing system cybersecurity. So unfortunately, cyber attack events in these systems are not new. Here's a timeline of cyber attacks targeting industrial control systems in general. So I forgot to explain the previous slide. So here's the representation of the manufacturing system. I have the physical processes, multiple processes that are enabled by the sensing and actuation, which is controlled by the distributed control system that is connected with a higher level control and management systems through the local area network, and sometimes they're connected to the cloud services through the internet. And this part, if this is a manufacturing process, it's IoT-enabled manufacturing process. If it's a power system, then it's a smart grid, and if it's a water treatment system. So all of this part is, in general, called an industrial control system. And these attacks are targeting industrial control systems in general, and many of them have caused significant physical damage, especially the one that started it all is called the Stuxnet attack that caused the centrifuges to explode and fail in a nuclear power plant in Iran in 2010. And since then, these attacks have been emerging, and these red ones are all related to the manufacturing sector. And you can see that there are more and more attacks on manufacturing industry. And actually, since 2021, manufacturing industry has become the top target of cyber attacks in all OT-related industries. So OT is operations technology. All right. So the cyber attacks or the cybersecurity events I'm focusing on are called cyber-physical attacks. So I'm not interested in, or at least right now, not studying the IP stealing, network spoofing, things like that. I only care about the cyber attacks and the internal sabotages that breach the network in order to cause physical damage to the operations, to impact the physical operations. And I want to introduce a new concept called cyber-physical resilience. And this is not a concept proposed by me. It's proposed by the President's Council of Advisors on Science and Technology last year in March. It's called Cyber-Physical Resilience, and it emphasizes the system's ability to endure the attacks and events and minimizing the ripple effects and ensuring the continuity of operations in degraded states. So the key assumption of this concept is that attacks and failures are inevitable. So the past research, including some of the works I've done, usually people follow the logic of, here's a system, let me find a new attack that is more stealthy, that is more impactful, or based on the specific attack, let me design a new detection algorithm. Let me design a better resilient control strategy. But those all rely on the knowledge about the attacker. But if we're assuming that the attacks and the failures are not inevitable, then we need to take the system as a whole. We need to consider all of the vulnerabilities in the system in a holistic manner, and we need to integrate the cyber and the physical components to study the weaknesses or the vulnerabilities or the risks of these systems. So we focus on the system ability to withstand extreme conditions. So we want to find, the first thing is we need to understand what are the extreme conditions. And then we focus on the extreme conditions to design our detection and mitigation strategies. All right, so this is for saying that the attacks I'm focusing on are intruding into the network and actually targeting the physical process. All right, so my research surrounding this cyber-physical security and resilience can be categorized into three aspects: the risk assessment, detection, and recovery and resilient control. And finally, I'll give you a summary. So the first work I'm going to talk about is an integrated cyber-physical risk assessment framework for worst-case attacks in ICS, industrial control systems. So this is about, I just explained earlier that the necessity of understanding the extreme case, AKA the worst-case attacks in an industrial control system. So the objective is to develop an integrated model for assessing the risk by modeling the worst-case attacks. And this work helps us interpret the cyber vulnerabilities into physical outcomes. And one thing that all of the manufacturers are facing when they're trying to study cybersecurity, especially the practitioners, is that they know there are vulnerabilities in their IoT network. And they invite the cybersecurity experts to analyze their network, and they probably tell them, you need to enhance your access control, you need to encrypt your data, but no one tells them what would be the worst consequences if there's a smart attacker that can utilize a specific subset or has knowledge about your system and cause physical damage. What would be that worst case physical damage that any attacker can possibly cause with a specific budget and resource? And so this is the thing we're trying to do. We're trying to model that rational and worst case attacker. And so the attacker's rationale would be a smart attacker, think about it. They will try to maximize the physical damage, but they have a limited budget. So they want to minimize their effort in terms of cyber exploitation. So that's the rationale of the attacker. And by identifying the worst case attacks, we can gain some insights for the further mitigation strategy. Hear me clearly? Yes? Okay. So the challenges mainly lies in the complexity and heterogeneity of cyber-physical systems or IoT manufacturing systems. The complexity comes from there are multiple components, cyber components, and the physical components. They work in synergy. They are correlated. They're closely coupled with each other. So that's the complexity of the system. And the heterogeneity means that the cyber components, the cyber network, and the physical process, they follow mathematically, they follow drastically different models, right? So we usually use a graph to represent the cyber connectivity, and we use state space models, system dynamics models to represent the physical process. So how do we integrate those models in one problem is a challenge. And the existing work in the industry, in the literature, is focusing on mainly trying to tackle these two aspects of the problem separately. And I really appreciate Laura's talk that inspired this work. Most of the work in the cyber layer will use a so-called attack graph, a directed graph to represent the cybersecurity state of the system. And on the physical aspect, people will analyze the process, the control behavior, the performance in terms of reliability and product quality. And there's only one work that considered both cyber and the physical components in one paper, but they still took a two-step approach. So they first found what will be the shortest path or the most likely attack in the cyber layer, and then I'll analyze the physical impact of this specific attack. But that doesn't necessarily, that most likely or fastest or easiest attack in the cyber layer does not really lead to the worst physical impact. So we have to integrate these two, and this is what we're trying to do. All right, so the method that we're doing is we still take the classic attack graph to represent the cyber layer. It represents the vulnerabilities and exploitations and the security states. I'll give you the details later. And we use the classic state space model to represent the physical process. And the key is to find the linking variables that appears in both this model and this model. And with these models, and we define the constraints and the objective of a rational attacker, we can formulate an optimization problem. And by solving that problem, we get a sketch of a worst-case attacker. So some definition, an attack graph is a directed graph. And the set of nodes, each node represents an attack state or a security condition. And the arc, each arc is representing an exploitation or representing a vulnerability. And these arcs are assigned a weight, and that's called Tij. We use it to represent the time that it takes to do the exploitation. So imagine an attacker, it's the system state, security states starts from benign, right? It's not under attack. And the attacker intrudes into the system and take sequential steps of actions of exploitation of different vulnerabilities to reach a set of state that enables the access to the sensor and control data. The reason why we consider sensor and control data is that's how they can cause physical damage. By manipulating those data, you can cause physical damage to the process. But in between, these steps that are taking, that the attacker is taking, is represented by the arcs. And by taking one step or taking one exploit, the attacker reaches, or the system reaches a new security state. And you take further, the attacker takes further actions, and the system goes to different security states. So, and it's a OR-type precondition, meaning that for the system to reach a specific security state, only one of the arcs directed to that node needs to be exploited, not all of the arcs directed to that node. So that's the OR-type condition. So this is the cyber model. And under this model, the attack model is a feasible path. So the attacker exploits vulnerabilities, as I said, to reach a set of the attack states. They're colored blue in this graph. And each of the state is corresponding to one channel of control or controller or sensor. So as long as the attacker can reach a subset of this set of nodes, then we call it a feasible attack. So the attacker is represented, or the attack actions, is represented by the set of indicator variables, Yij, each representing whether each arc is exploited by the attack. And whether it is feasible is represented by taking the sum of the multiplication between Yij and Fij, where Fij means the number of target states reached when vulnerability Ij is exploited. And based on that, we can also derive the time that this attack reached state, this attacker reached state I for each of the security state. So that fully defines the attacker's action in the cyber layer. All right, so then we move on to the physical model. So many of you probably is very familiar with the state space representation, where we're using the vector x to represent the system state, and the state evolves according to a Markovian process based on the control input u. And the measurement z is a linear function, we assume, of the process state. And obviously, these two are the noise terms. And we're assuming that the control action is a linear function of the sensor measurement, just for simplicity. And aside from that, the system dynamics model, we are also using a degradation model, where the degradation signal S is a Brownian motion with a drift. And this drift is actually a function of the system state. So imagine the attacker has caused a successful attack in the physical layer. So the attacker manipulates the control action, and that will change the state of the system. Think about a rotating bearing. The attacker changes the rotation speed secretly. And so the actual state of the bearing will change, and that will actually accelerate the degradation of the bearing. So that is through this function that connects the state with the degradation rate and the degradation signal. And so we can derive the distribution of the degradation signal, and we can derive the failure time, which is the first time that this signal crosses a specific threshold. Okay, so that is the physical model. And in the physical layer, the attacker's model is characterized by the AT and BT variables over time. So over time, as soon as the attacker gains access to a sensor or a controller, the attacker can start manipulating the sensor and controller data, and they're modeled as adding a bias to the original data, to the true data. So that's the attacker's model in the physical layer. And what about the constraints? So in the network, I kind of talked about the constraint. It has to follow a feasible path. And we are assuming that the attacker has limited budget. Otherwise, the attacker will just exploit all of the vulnerabilities and manipulate all of the data. But obviously, that's not possible in reality. So we're assuming there's limited time allowed for the attacker to take all of these actions, including the actions in the cyber and the physical layer. And then the attacker has limited access, and we're using a number k to cap the number of sensors and controllers in total that the attacker can access. And so that's the network constraints on the attack. And the physical constraints include, well, the sensor measurement after or under the attack cannot exceed a certain range, a certain bound, and that's natural to any physical process. So that's modeled by this L infinite norm of this Z vector. And the manipulation vectors AT and BT cannot be too aggressive, because if you drastically change the control and the sensor, it will be easily detected. So for the attacker to bypass any intrusion detection algorithms, we are bounding the AT and BT within some upper and lower bounds. So those are the constraints. And then we move on to the objective. The objective of a rational attacker is to maximize the utilization of this limited resource to maximize the physical damage and minimize the effort, right? So maximization of the physical damage is represented by minimizing the failure time. So I want to fail the system as soon as possible. If it fails earlier, then I have brought a larger physical damage is the rationale of the attacker. And the effort in the cyber layer is just a function of the exploitation actions, whether it took the action or not. So minimizing the time of failure and minimizing the effort is the objective of the attacker. So here's the final optimization model. The blue parts are the objective and the constraint related to the cyber network, and the red parts are related to the physical process. And you can see some variables that are, a little bit brownish color. So these are the connecting variables. So these alpha and beta, alpha I and beta J represents, it indicates whether a sensor I or controller J is accessed by the attacker. So it is constrained by the accessibility in the network layer. So these variables, they appear in these blue constraints. They also appear in the red constraints because they're used as if you don't have access to a sensor, then you can't manipulate it. So if alpha is 0, for example, then your AIT has to be 0. Does that make sense? And the same thing for the controller. So alpha and beta, they both appear in the cyber constraints and the physical constraints. And that's the key of integrating the cyber and the physical models. And if we solve that problem, what result does it give us? How can we use this model? So first thing is we can understand how a rational attacker or worst case attacker behave differently under different budgets, okay, under different resource limitation K and different levels of T. So we randomly generated, this is a numerical study, so we randomly generated 3 attack graphs, and each with different level of connectivity. So this one is most dense and this one is more sparse. And we borrowed parameters from previous work on bearing rotating test bed. And here is the different distribution of failure time under different levels of T and K. And you can see when it's normal, the system roughly fails at 600. But if you increase, if you allow 200 steps of the attacker's action, then it decreases the failure time. So it accelerates the failing process. And if you give the attacker more budget for K, and obviously the failing time will be decreased. And further, if you increase T, that will decrease the expected failure time. And this one is more clear under different levels of T and K. We plot the mean time to failure, right? So that gives us a monotonic decreasing behavior as T and K increases. So what this tells the operator, if we look at, let's say, a certain level of K, there is an elbow of T, right? So if the attacker is given the budget, then I probably don't want to allow allow the attacker more than, in this case, I don't know, 600 time steps. And what does this tells us? So we don't want our detection algorithm to be less frequent than 600, because if the attacker has as long as 600 time steps, then it can cause this amount of damage in the worst case. So in the design of my detection algorithm, probably I need to increase my, my frequency so that the maximum time allowed for the attacker is probably below, let's say, 200, so that the maximum damage is not significant. So this is how we can use this to guide design of a detection algorithm. And we also want to know how our model work in the real world cases. So we borrowed a case study from the literature of a water boiling power plant. There are the water inflow, and we're heating the water, and there are water levels, and there's a steam valve connected to a generator. And it's connected to an IoT network, and the model of the IoT network is given, luckily, from this paper. We also want to know, how does the performance of our rational attacker model compare to the models in the literature? So these are the two benchmark methods we're going to compare with. Before the comparison, let's look at the results of running our model on this water boiling system. So if you look at these 3 points, you can tell that at t equals 400, that's probably the worst case, so I don't want to give the attacker more than 400. And in terms of different k levels, if you move from this point to this point, you can tell that, oh, okay, so when k equals 1, this is the sketch of the actions over time, so AT and BT over time. So none of the controller is under attack, only one sensor is under attack when k equals 1. And if I move to k equals 2, another sensor is under attack. And so these two sensors are water level sensors. And so if I have as an operator, as a defender, if I have limited budget to encrypt a selected number of sensor channels, then probably these two sensors are the first I need to consider encrypting, because these are the ones related to worst case attacks. If the attacker accesses these two sensors, it will cause significant physical damage. So this is how we can, use this framework to guide the mitigation strategies. All right, then comparing with our benchmark method, as I said, this paper by Huang in 2018, they focus on both the cyber and the physical models, but in separate steps. So this is the model they defined in the cyber layer, and they kind of analyze the physical impact of this attack. And so we're implementing this attack in our framework and see what's the physical damage. And then there's another paper that's published very recently that also runs an optimization problem, kind of trying to model the worst case attack behavior. But their assumption is that the attacker has already gained full access to all of the sensor and control channels. So they're not able to identify the critical components, but they are able to solve for the AT and BT solutions in the physical layer. But this is the damage function they define. So they're trying to minimize or trying to maximize the difference between the expected sensor data under attack and the target value. So that's how they quantify the damage. And so if we run our algorithm and we compare the value of the damage function using this papers, so we solve for our objective function, but we're comparing the value of the solution under this function. And we find that it's actually close. And besides that, our solution still follows the engineering intuition, meaning if we have a higher T or K available to the attacker, it is going to cause a worse damage according to the metric proposed by that other paper. So this is what we found, and that reassured our modeling kind of logic. And if we compare the damage using our metric, which is the failure time, then obviously our method outperformed the methods in the literature under different K and T levels. Okay, so that's about it for this work. And there are some limitations about this work, I have to admit. So we are now considering the simplified model for the physical process. We're using a linear time invariant system dynamics, a state space model. So this model we can use it to represent a relatively simple process, but if we really have a very complicated multi-stage, multi-component system that are loosely intercorrelated, and there are a lot of different channels, so the dimension of the state of the system is high, then a state space model may not scale up very well. So the solution would be consider some data-driven machine learning models to represent the dynamics of the process and how do we incorporate that into our optimization framework? And in the quantification of the physical damage, we're now only considering the reliability, the failure time, but we can also take the safety and the product quality into consideration for a more comprehensive quantification of the physical risk. And we're also ignoring some of the uncertainties in the physical process in our current optimization framework. But in the future, if we want to take that into consideration, then the attacker is not really making all of the attack actions, decisions all at once, but making sequential decisions based on its current observation of the system behavior. So that can be modeled as a state continuous action MDP problem that can be solved using some reinforcement learning techniques. And finally, we can also take the success rate, the uncertainty in the cyber layer of exploitation into account. So that's the future directions along this road. But I really like this work because this is the first one that actually integrated the cyber and the physical model. And the model is actually very flexible, and there's a lot of ways to modify it to be more comprehensive and to be generalized to more applications. So that's the risk assessment. And then let's move on to cyber attack detection. I've actually done a lot of work in detection during my PhD. Here I'm focusing on multi-stage manufacturing system. So it is a series of interconnected components, stations, or stages working together to produce the final product. So it applies, this multi-stage model is actually very widely applied to both continuous and discrete manufacturing processes, like pharmaceutical manufacturing, assembly processes, and steel making processes and things like that. A problem, well, here is a typical model. Again, we use a state space model for each stage. So this subscript K is no longer the time index, but the stage index. And for each stage, there's a controller, and we have a Kalman filter. That's the optimal linear, Bayesian state estimator that's coupled with this LTI system. So think about the process like this. The raw material goes through each of the stage sequentially, and the output of the previous stage is the input to the next stage. And for each of the stage, there's a controller that takes the measurement from the previous stage as input and makes the control action decisions and so on and so forth. And they are making this decision not just based on the measurements, but also the reference points, the target points, the control targets, that is sent from the supervisory control system. So here's the setup of the multi-stage manufacturing process. And the attack we're considering is called false data injection attack. So in this type of attack, it is very common as long as the attacker gains access to the sensors, they will be able to implement a false data injection attack. And it's modeled as just adding a bias to the true sensor data. And these attacks can be actually designed to be very stealthy, because if we're just doing a linear regression type of state estimation, then this can be easily designed to bypass that type of detection algorithm. So we use 4 vectors for a 3-stage process, 4 vectors to represent the attack. And the challenge of detecting a false data injection attack in a multi-stage process is that this multi-stage mechanism allows the attack to propagate throughout the different stages, right? Think about an attacker that happened in the earlier stage. If it bypassed the detection in stage 1, and you don't really measure anything related to the aspects or the variables under attack until a later stage, and you won't be able to find it, and probably you had some process that interplays with the variables under attack, and that will amplify the impact of attack in that way. So therefore, the distributed detection algorithm may not work, especially if you have a later stage detection algorithm and you detect something, you won't be able to tell which stage actually is under attack. And there lacks a generalizable framework to not just detect, but also identify the stage that caused the attack, right? The stage under attack. And the literature in cyber attack detection can be divided into, the model-based and the data-driven methods. So for the model-based methods, they're more interpretable. They are less scalable. The good thing is that they use the system dynamics model, so they don't really rely on a huge comprehensive set of training data. And on the other hand, the data-driven attack detection algorithms, they rely on machine learning, so you better have a good training set. And it's usually a classification model, so it tells you whether the system is under attack or not. And so if you see an alarm, you still won't be able to tell which stage caused this alarm. You can't root cause because of the bad interpretability of these data-driven models. So we want to actually combine the benefits of both the signature-based and the anomaly-based methods. So we want to still utilize the information from the system dynamics model, and we want to also utilize the data, the features that we can extract from the data to get a more accurate and interpretable conclusion of the detection and localization. So here is the method. The traditional model is, if we collect all of the sensor data, we can project it onto the column space of the measurement matrix H to estimate the state X, and then whatever is left is the residual. So if the residual is large, it means not all of the information in my sensor data can be explained by the state. So that means probably there's an attack. And so the detection algorithm is run on the residual, the magnitude of the residuals. So the bad thing about this, in this setting, is first the Xi and Xj are correlated. These states are correlated because your decisions are made based on the previous states. And also, we're not able to identify the stage under attack when we see an alarm later. So here's the proposed method. So if we can decompose our sensor data into two column space, one is not the original state space, but I call it auxiliary state space that includes the raw state, the state of the raw material, and all of the input from the supervisory control, all of these reference points. So this makes sure that all of these information are external to the sequential process. And so whatever left is to be explained, the uncertainty left to be explained is by the attack. So the only other external input to this entire process is the attack. So if I can project it onto the column space of the auxiliary state and the attack state, then I can estimate or reconstruct the attack features. So the exact values are injected to each stage. And so naturally, whichever vector that stands out will represent the stage under attack. So that's the logic. And so we formulate this as a group lasso problem. So we can actually derive these two matrices from the system dynamics model and the attack model. And we'll try to minimize the L2 norm of the residual, whatever is left cannot be explained, and the group-wise L2 norm, summation of the group-wise L2 norm of the attack features, deltas. Okay? So if we solve that and we get the solution delta, then the larger delta will correspond to the attack, the stage under attack. And if there are two scenarios, if your X tilde is known, then the solution is very straightforward. You just subtract whatever is multiplied by X tilde and H, then we solve this problem. If X tilde is unknown, which is usually the case, then we'll have to make sure that this space is perpendicular to the column space of H. So we'll have to extract the subspace from H1 that is perpendicular to H and reformulate the problem. But that doesn't significantly change the algorithm that solves this problem. So if we solve this iteratively for each time step, we are identifying the stage under attack as the one with the smallest p-value with the chi-square test. So after we get the estimate of delta, then we can reconstruct the residual vector, and we run a chi-square test on this one. Okay, so here's the entire framework. We're trying to combine the information from the data and the domain knowledge to formulate this, what we call a hybrid attack detection framework. And if we compare it with the traditional group-wise chi-square test, you can see that the detection delay, this is the run length, the detection delay basically, for our method is lower than the traditional method. But the major advantage is really in the localization accuracy. So when the attack is on stage 0, you can see that the localization accuracy for our method is significantly better than the traditional method. And when it's later stage, and obviously both of them will, the traditional method will have an increased accuracy. And we run it on also a case study that we borrow the data from this very old paper on SUV door panel assembly process, and the advantage is even more significant. Okay, so that's on the detection. And the future directions, I want to spend a little bit time on the future directions. I don't know how much time is left. 10 more minutes? Okay, cool. I really do think that in cybersecurity space, we need to reconsider or rethink about the attack detection algorithm design logic. So right now, what people are doing, as I said, is if you're given an attack, then I'll design a detection algorithm specifically for that attack. And there are two ways to design a detection algorithm. One is you have all of these data from different components, different processes, different equipment, and you dump it in to a large, complex machine learning model. And hopefully that will classify whether the system is under attack. With enough training data, probably this can lead to a very high accuracy. So it has a high coverage, tells you accurately whether the system is under attack or not. But that doesn't really give you much insight to what to do next. And you're not guaranteed to maximize the resilience of the system with this type of algorithm. And on the other hand, you can have multiple local algorithms, each monitoring one process. So then you can leverage more of the domain knowledge because the system is, or the model is less complicated. So they will have a low coverage. The model will be highly interpretable, and it has a low computation complexity compared to this one. But as I said, because of the synergy between the process, such as the multi-stage process, you're not guaranteed that an alarm raised by a certain model is specific to that process that is monitoring. False alarms will be triggered by the other correlated processes. So the logic is we should still collect information from different processes, but we should be selective in terms of we only care about the critical information that is more important for the resilience of the system. So remember what we did in the first part? We identified the critical components, the critical data channels, and those can be used as a selection method for formulating this optimal detection algorithm. Because the critical information we identified are correlated with the worst case attacks, this model will be naturally more sensitive to the worst case attacks, to the high impact attacks. And probably this is coming with a trade-off of giving an easier win to the low impact attacks, but overall, it improves the resilience of the system in the best way, in the most efficient way. So that will be the resilience-driven attack detection. So that's the next step in the area of detection. And finally, I just want to briefly mention the resilience control and the automatic recovery. This is ongoing and future work, so I don't have a paper to present, so don't panic. I'm just a few slides towards the end. So here I'm thinking about a replay attack. In a replay attack, the attacker records a period of normal sensor data. And during the attack, they will manipulate the attack actions and replay this recorded normal data. So as the operator, as the detector, you will only observe normal control data and the normal sensor data. And so it's hard to detect this type of attack. And what people have came up with was using what's called a watermarking agent that injects an authenticating signal to the original control action. And the detector will check whether the sensor output is closely correlated with this authenticating signal. It's basically a white noise that is only known to the operator, but not known to the attacker. So if it's correlated, then obviously that's fine. And if it's not correlated, then that means the control action is being manipulated. So that's the logic. But this causes an issue because if you want the detector to be more confident, to have a higher power, then you need to inject a significant amount of watermark. So you inject a significant noise to the optimal control action. So that will compromise the performance of the controller. And so if we don't want to do that, we want to do it in a smarter way, then we should do it in a dynamic manner such that the detector tells the watermarking agent whether I'm confident about my decision. If it's less confident, then I'll increase the intensity of the watermark. If it's more confident, then I can decrease the watermarking intensity to guarantee a better control performance. And one step further from that, because we already have some, smart agent or reinforcement learner, and if we can utilize some side channels that is actually monitoring the plant through a secured channel, then we can get some vague information about the ground truth, what's actually happening. And so if the RL agent can utilize this information, we can make the watermarking signal a corrective watermark. So that corrects the manipulated control action. So that's about the resilient control, automatic recovery, actually. And this is about resilient control. This is even further in the future, but the idea is if we have many, many processes correlated with each other, it's a curse because it allows the attack to propagate, but it's also a bless because if one of the components is under attack, we can utilize this correlation, the information at other processes that is related to this one to still be able to control this process under attack. And this can be done through federated learning, but not the traditional federated learning where you assume that different parts of the data set is preserved by different agents that are heterogeneous, that are homogeneous. But here you have different processes, so different processes preserve different parts of the features of the data set. So you're dividing the columns, not the rows of your data set when you're doing vertical federated learning. So that's the next step. And in summary, so here are some extensions of some other projects I'm doing in the power system, trying to develop a more resilient, bad data resilient detection framework. And in healthcare and human factors, trying to detect an attack on a surgical robot using physiological sensors. So here's like a map of my research. I focus on 3 thrusts, all related to cyber-physical security and resilience. First is about resilience quantification, attack modeling, risk of quantification, worst-case attack modeling. Second is about detection. I'm dividing it into 2 pivots. One I just mentioned, and the other is related to human-centered attack detection. So because I realize in a lot of real-world settings, recovery or response to cyber attacks often involve human in the loop. So how do we make this intervention system more friendly to this kind of setting, and how do we train the manufacturing workforce in the best way for manufacturing for cybersecurity awareness, and using physiological sensor data for enhanced attack detection, and finally the resilient control I also mentioned. So my current I think we briefly mentioned that my current funding comes from NSF, and in the future I'm going to focus on building the connections with DOE, ONR, and DHS. So that's it, all of my presentation. Thank you so much for your attention.
Thank you, Dr. Lee. So great timing. We have plenty of time for questions. So, but I ask that if you want to ask a question, raise your hand. So I'll bring you the mic, and we can have it in the recording.
Thank you so much. This was great. And I was very excited when you talked about the human-centered, cyber attack detection. And you mentioned using physiological sensors. We have done some work in that. One of the questions I had for you is, yes, we want to look at how we can use humans. The idea over here is to see how humans respond to a cyber attack and then how they sort of react and use that information to improve. Have you looked at the other side, which is when humans actually make the systems more vulnerable due to some systems error? Can we predict that or forecast that when humans are more likely to actually create vulnerability in the system rather than more in a reactive way?
Oh, that's a very good point. Actually, to be honest, I never thought about that aspect about human error, but I fully understand what you're trying to say. With the human in the loop decision making, I guess that's loosely connected to this part of the intervention system design. So what we're trying to do is to design, because in the past, or what I've done in the past for detection is we just care about all of the things until an alarm is raised, right? So I'm just trying to improve the accuracy, improve my algorithm so that I can raise a correct alarm. Yeah. But sometimes it can be a false alarm. There's always a possibility that it's a false alarm. And it's the human that receives these alarms sequentially and makes a decision of what to do with the system. So that intervention to the human, how they can receive the right information so that they can calibrate their trust, I'm throwing out buzzword, but they can calibrate their trust towards this detection algorithm at the right level. I think that follows the same logic of human error of, the human needs to develop the right trust to the machine and make the right decision is what we're trying to study. Thank you.
Thank you. Great presentation. I have a few questions about the first subject that you mentioned.
Yeah.
First, a fundamental question. The network that you are considering, the attack network, is that internal to the manufacturing systems, or is it just like a network that is going on outside the organization and just there's one entry point to the system? Or
absolutely. So it is. So part of it is connected, probably this higher level part is connected outside the factory, let's say.
Okay.
It's probably connected with the other organizations or other facilities in the same organization and to some third-party service. But the SCADA system is always on site, and this involves also some, local area network that transmits the sensor and the control data to the local on-site, management supervisory computers to make monitoring and maintenance and control decisions for the process.
So the network you are modeling is really the internal, like the ARCs are really within the control of the SCADA system, right?
You can take it that way, and it's pretty flexible. If there are vulnerabilities that allows the attacker to get access or intrude the local networks through the internet, then that can also be taken into consideration.
Okay.
Yeah.
The second question is, I was also like, the immediate question I had when you present the model is you're only considering a single-time attack, but then you said that's one of the current research that you are working, like a sequential attacks, which I think is more reasonable, right? I mean, but then, and I know this is sort of ongoing, but I'm very curious, being also an MDP guy, like, do you think that you can have like a very longer term horizon in that MDP model that you are thinking? Because I feel like even ignoring the physical systems, people are struggling the moment you go beyond like 3-4 attacks, like 3-4 stages in the decision, it just like gets out of control. I mean, did you ever think about that?
First of all, if you're talking about one-time attack, I just want to be a bit more.
Maybe I got it wrong. Yeah.
So if you look at, let me see here. So the attacker in our case makes the all of the decision of manipulation, the actions in the future, it makes one-time decision.
One-time decision.
But it's not a one-time action.
Yes. So, but I'm talking about like once the attacker receives feedback, updates the, sort of attack strategy because unsuccessful in this arc, now I go to the next arc. So that type of decision, do you think you can go with like longer term?
Oh, yes, I think so, especially that will be a part of the future work, obviously, but we're thinking not just about, it is continuous state in the physical layer, but in the cyberspace, it's still making, so the attacker's action space is actually a mixture of discrete decisions regarding the exploitations and the continuous decisions regarding the manipulation. So that's kind of creating a very interesting RL setting of, mixed space. So we're doing some hierarchical RL, borrowing something from the literature, but it can be like a continuous process of the attacker receive some feedback either directly from the sensor data or its prognosis of the system based on their knowledge about the physical process. Yeah.
Can I ask one more quick question? The numerical experiments, how do you find data? I noticed that you got from the literature, but in this space, like, is it easy to get data to test your models?
Well, okay. So I think for the physical model, it's very easy to obtain. So this one, we're lucky to find a work that actually provides us with the IoT network setting, and we'll be able to find on open source website, CISA, that listed all of the vulnerabilities, and actually the authors found the vulnerabilities related to that IoT network. So that's a necessity, and obviously the physical dynamics usually is already there, is easier to obtain. What's challenging is about the cyber layer, because not all of the IoT-enabled processes, they will publish exactly their network configurations and what exactly device and protocols they're using. So.
Okay, great talk. So I recently also started a project in the cybersecurity, and during our meeting with those domain experts, they asked me a question, like you can do anomaly detection, but how could you differentiate if this, there is a change in the sensor signal really matters? Because some change in the sensor signal may cause some disruption in the production process, but some change may just like a random perturbation. So how could you differentiate in this anomaly detection algorithm? Have you considered that?
Well, not in this work, but definitely. Actually, my first work was on differentiating cyber attacks from faults, from sensor faults, controller faults, degradation. So the key, or the core of it, is actually to extract not just the alarms, but the underlying data features or the data structure. So to identify the subspace that is representing the attack. So that subspace, if I really have to talk about the intuition, would be there's always something artificial and intentional behind the attack, unlike a fault or a degradation that will, first it will follow the physics, and also it's more random. So one way is to understand that key feature difference in the data when you consider all of the data channels jointly instead of looking at a single channel. That's one way. And the other is to incorporate the network data. So there will be some trace that the attacker will leave in the cyber network, and if we can build a causal relationship between the cyber activity and the sensor data, that's another way. And the third way would be, I don't really care about the difference, I'll just care about the risk. Whenever this sensor data changes, no matter if it's because of an attack or a fault, it will cause a physical damage, and I should take care of it. So.
Okay. Can I ask one more question? Okay. Yeah, so I understand the cybersecurity, once you have the system layout, right, and you can do a lot of assessments and anomaly detection. But the challenge I see is if you do not know how to design the system, in that case, I talk about how could we build a more resilience like a system. So have you thought about the like feedback loop? So once you know how to detect, once you know how to assess, how do you feedback into the design stage? Have you done anything like that? Oh,
no, not at this stage, but I think it's related to what we're thinking about is enhancing because in reality, I would assume that the IoT network is kind of preset. The design part is about mitigation, is about encryption, is adding side channels or encrypting data channel or using a more secured protocols on top of this connectivity design. So if we don't change the connectivity design, all the decisions that we make is about mitigation. So the mitigation problem that Jim talked about with me yesterday, that you can formulate a similar optimization problem on the operator, the defender side, just as what I do for the attacker. So the defender will also try to maximize the utilization of the resources to allocate the mitigation on the network in order to reach the maximum resilience. So I don't know if that answers your question.
Well, we better wrap it up. Hopefully we have time for follow-up questions and stuff later.
Okay.
But thank you very much again.
Thank you. Thank you so much.
Good.